Welcome to The Explainer. I'm Dr. Chem, and today we are diving deep into chromatographic parameters and theory. Let's jump right in.
So I've got a question for you right off the bat. Is chromatography merely some kind of fancy laboratory filter for separating stuff, or is it actually a highly sophisticated mathematical language? I really want to challenge your basic assumptions here, because when you look at a chromatogram, you aren't just seeing random bumps on a baseline. No way. You are looking at a deeply structured narrative. Literally every single peak carries hidden, completely decodable information about molecular movement and quantitative control. Our goal today, to translate those peaks into their underlying physical truths.
To actually understand this language, we first need to establish the basic setting of our molecular journey, right? Every chromatographic system relies on a dynamic tension between two very different phases. On the one hand, we've got the flowing mobile phase. This is a fluid, maybe it's a gas, maybe it's a liquid, that actively sweeps through the system. And on the other hand, we have the immobilized stationary phase, which is essentially a coating on a supporting medium packed inside the column. So the absolutely crucial point to take away here is that separation is entirely based on relative affinity. Molecules that have a stronger affinity for that stationary phase, they're going to be held back. They move much slower, while the ones that prefer the mobile phase will just race right ahead.
Now, this concept of affinity brilliantly translates into measurable time. The primary metric we use is retention time, which we call TR. Think of this as the total journey. It's the total time elapsed from the exact millisecond of injection until that analyte's peak maximum actually hits the detector. But we also have to account for dead time, labeled TM. That represents the baseline speed of a completely unretained species. It essentially tells us how fast the mobile phase itself is moving through the system. And the difference between those two, the adjusted retention time, or TS, well, that's the actual time the molecule spends interacting with and being held back by the stationary phase.
Okay, let's build from pure time into something even more powerful, a fundamental measure called the retention factor, or K. You might also hear folks call it the capacity factor. By taking that adjusted retention time, the time spent stuck to the stationary phase, and dividing it by the dead time, we get a ratio. So why does this matter? Well, because it gives us a mathematical number for a molecule's physical preference, completely independent of things like our column's length or our flow rate. It's all about the balance between phases. If K is too small, the molecule is eluting way too rapidly for us to accurately measure it. We are literally putting a universal value on a microscopic interaction. It's pretty amazing. Moving right along, we are really building the mathematical pyramid now. Once we have the retention factors for individual molecules, we can compare them to figure out our selectivity, denoted by the Greek letter alpha. Selectivity is simply the ratio of the retention factors of two adjacent peaks. It asks a really simple but profound question. Do these two analytes differ enough in their relative interactions with the stationary phase to actually be separated? Because even tiny, microscopic differences in a molecule's polarity or charge can lead to a perfectly measurable difference in retention. If alpha equals exactly 1, well, their retention times are identical and they will stubbornly coelute as just one single blob. And that brings us to the ultimate practical goal of any chromatographic method, resolution, or RS. Resolution is the defining mathematical parameter. It's the one that tells us if our separation was actually successful in the real world. This single concept beautifully encompasses everything we've been talking about. It unifies the ideas mathematically, combining the column's efficiency, its selectivity, and its retention capacity into one single powerful number.
To truly appreciate resolution, we have to visualize it. Take a resolution of 0.5. At that level, you just have a blended, overlapping blob. There is no way you can confidently quantify two distinct peaks there. Now, as a resolution increases to 0.8, a little valley forms between them. It's better, but it's still not quite enough. Down at a resolution of 1.2, we're getting very close. But for a truly complete separation, where the peaks return cleanly to the baseline, allowing for perfect quantification, we typically require a resolution greater than 1.5. Why does a resolution of 1.5 matter so much? Well, in the real world, it's the difference between passing a safe pharmaceutical drug and failing it.
So if high resolution is our primary goal, we absolutely must confront its worst enemy, band broadening. We're going to shift our focus now to the internal physics of the column itself. When you first inject a sample into a system, it starts off as an incredibly narrow, highly concentrated zone. But as those molecules travel down the length of the column, constantly interacting with the packing material, that initially narrow injection zone inevitably widens. It just starts to spread out. Think about the physical space inside the column. As the analyte moves through the packing material over time, it physically spreads. It starts tight and then gradually diffuses outward. And this internal spreading translates directly to those wider, less efficient, and shorter peaks you end up seeing on the detector signal. The wider the peak, the harder it is to separate it from its neighbor. Plain and simple, band broadening ruins resolution. Which brings us right to the mathematical countermeasure to band broadening, and that is column efficiency. Column efficiency is a measure that describes exactly how much a peak broadens as a function of how long it's retained in the system. Narrow peaks indicate high efficiency, right? Our objective in laboratory method development is always to keep band broadening to an absolute minimum. In a real-world lab, whether you're testing drug purity or analyzing forensic evidence, high efficiency directly leads to vastly superior separation performance and much cleaner, more reliable data. To ground all of this mathematics in some scientific history, let's quickly trace the theoretical quest to understand and conquer this column efficiency. The scientific community built some rigorous models over the decades. First, back in 1941, Martin and Singh proposed the plate theory, which gave us a really convenient way to measure performance. Then, later in 1956, Van Deemter, Zeiderweg, and Klinkenberg developed the rate theory, which actually gave us the tools to actively optimize that efficiency. Let's dive into Martin and Singh's plate theory first. What they did was brilliantly adapt a conceptual model borrowed straight from fractional distillation theory. They imagined the continuous chromatographic column as a series of hypothetical, highly discrete, thin steps, which they called theoretical plates. The core assumption here is that within each one of these microscopic plates, there's an instantaneous equilibrium set up between the analyte in the stationary phase and the mobile phase. The major takeaway from this conceptual model is what we can call the rule of plates. More plates, denoted by the letter N, equals higher separation power. It is a simple, undeniable correlation. The smaller the height of each individual plate, the more plates you can pack into a given length of column. And the more plates you have, the more efficient the exchange is between the two phases. In a practical lab setting, this is exactly why chemists will use longer columns or columns packed with much smaller microparticles. Doing that is a direct physical path to boosting analytical efficiency and generating those beautifully sharp peaks we need. But, plate theory doesn't quite explain why those bands broaden in the first place. For that, we turn to the 1956 rate theory, beautifully summarized by the Van Deemter equation. This is the central theoretical model, the modern predictive tool we use to measure the exact physical contributions to band broadening. It describes the relationship between plate height and mobile phase velocity through three key things: eddy diffusion, which is due to the multiple varying flow paths molecules can take; longitudinal diffusion, which is the molecular spreading along the column; and mass transfer resistance between the phases. By understanding these exact phenomena, chemists can actively predict an optimal flow rate. They can adjust variables like temperature, particle size, or mobile phase velocity to hit the exact sweet spot where efficiency is absolutely maximized. So, as we wrap up this explainer, we've seen how retention, selectivity, resolution, and efficiency all tie together into one unified predictive science. We've taken what looks like a simple laboratory separation technique and revealed the elegant mathematical language underneath. I want to leave you with this final provocative thought. If we can decode and precisely control the microscopic journey of complex molecules using these fundamental mathematical parameters, what limits our ability to quantify and control the macro world around us? Think about it. Thank you so much for exploring the language of chromatography with me today.